Hello everyone, it's me Nishan Paudel and welcome to my channel. If you haven't yet subscribed to my channel, please do subscribe. In today's video, I'm going to talk about common emitter amplifiers. We are going to study how the circuit works and how it amplifies a voltage at a load. So let's without any delay, let's get to the point. So a typical common emitter amplifier has a voltage source which is divided by two resistors R1 and R2. So this is one branch where it's divided, and there's another branch where there's a transistor and and at both transistor and at both emitter and collector there are two resistance. The resistor at collector is called RC and resistor at emitter is called RE. Both of them are connected to the ground, and from the collector there's a capacitor that's connected to the load voltage, and there's a load resistor. From R1 and R2, a voltage is divided, a VCC is divided at this point, and the divided voltage is connected to the base of the transistor. And at the same junction, capacitor is connected, which is in series with source resistance, a voltage source, AC voltage source. Vs is connected, which is connected to ground as well. So this is a typical common emitter amplifier circuit, and there's also a capacitor at RE, which we'll discuss later. So if we look at this circuit carefully, there are two capacitors, one at the source branch and one at the load branch. So as we know that the capacitors won't let DC pass through them, so only the middle section of the circuit will act for the DC source VCC. So let's analyze the DC voltage across this middle section of this circuit. So at this point, it's called VV because it's the base of this transistor voltage. I'll just write it at voltage at base. It's simply the divided voltage R2 by R1 plus R2 of VCC, right? So we know that transistors have a PN junction, so the base emitter potential drop is 0.7. So voltage at emitter at this point of the circuit is R2 by R1 plus R2 VCC minus 0.7. So we have RE here, so we can easily calculate the emitter current from this voltage at emitter, which is simply V by R. So current at emitter is simply 1 by RE times the voltage at emitter, which is simply R2 by R1 plus R2 VCC minus 0.7. I'm leaving a little gap here to count for the AC source later on. So we know at transistor, collector current and emitter current are nearly equal. So I'll just assume that the current at collector is also the same current as it is in emitter. So if the collector current is 1 by RE is this, then we can calculate the voltage at the collector, which is simply VCC minus voltage drop across RC. We know the collector current is this, so RC by this current is potential drop across RC. So voltage at collector is simply VCC minus potential drop at RC. So let's write that voltage at collector is simply VCC minus the potential drop at RC is IRC. So it's simply RC by RE. RC by RE, R2 by R1 plus R2 VCC minus 0.7. I'm still leaving a gap to account for the DC part later on. So this is the voltage that we'll get at the collector. So this is only due to the DC, but we also have AC source which we need to amplify at VL. So now let's account for the AC part of this circuit. So uh, let's suppose after certain drop at RS, the AC voltage that reaches this point at this junction of R1 and R2 is VV. For simplicity, we'll later account we'll also calculate the voltage drop at RS later on. But for now, let's suppose it to be VV. So the voltage at base is simply the voltage due to DC plus voltage due to AC, and voltage at emitter is also voltage due to DC plus voltage due to AC, right? So we can just add the AC part at every point of our formula, and we'll get the AC analysis of this circuit, right? So now if we look at the collector, we can calculate the potential due to AC part only. And if we look carefully, BCC is the DC part, this is DC and this is DC. Only this part of this formula accounts for the AC source. So the voltage at collector due to AC is simply which is VL, right? Voltage at collector due to AC is VL because it's short circuited for AC source. So VL is simply minus RC by I hope you can see it, RC by RE VB, and VL by VB, which is actually the voltage gain, is the base formula for voltage gain is RC by RE. Here we haven't accounted for the current that will pass through this section, through this capacitor due to the AC part, because it's blocked for DC but it's not blocked for AC. And we know the AC source has a sinusoidal waveform, right? A sinusoidal signal where it goes to positive and it goes to negative, and ground is 0. And if we consider VL, so ground is 0, this is ground. So at VL at some point there will be voltage higher than ground, so even yeah, so negative, so it will draw it, so BL will be ground and it makes this ground greater than the VL. So the current can flow through ground to VL to the circuit. So let's account for that and let's see how that acts. So we have VL here and it's connected to the ground through RL, and the capacitor is short circuited for AC, and we also have RC, which is also connected to the ground, because I'll just explain it. Because let's say this is ground, so there's a constant VC source, right? And there's a waveform of AC signal which will change this signal if we superpose them. So it basically acts as a ground where current the voltage changes through this base point. So we can consider it to be ground for AC signal. If it's not there, it will simply this circuit will simply act as a simple source, and this point will act as a ground. So we can consider VCC to be ground. So, and there's another part where IC, the collector current, flows through the transistor to the ground, and we know the direction of current is in this direction, so it's connected to the ground. And this is AC part of the collector current, and we know the current at collector is 1 by RE and R2 by R1 plus R2 VCC minus 0.7 plus VB, and the AC part of it is simply VB by RE, right? VB by RE. So what we get here is, and VB by RE equals to the resistance, the equivalent resistance of RC. These two are in parallel, so equivalent resistance is RC by RL, right? So B equals to IR. This is I times this is equivalent resistance, RL is the potential here, and it's negative because the current is negative, it's flowing in the opposite direction. So what we get is VL by VV is RC RL divided by RE RC plus RL, it's negative. So this is the base amplification, and we get the same base amplification here times RL by RC plus RL when we account for account for AC current passing to and fro in this branch. So this is the amplification formula. So now let's move on to something else. So for now, okay, so now, so I have made this figure already. For now, we consider, so we know that the amplification depends on RC by RE, right? So if we add a capacitor, to this branch, what we observe is that for DC signals, DC cannot pass through this capacitor. Let's say this capacitor, let's name this capacitor CE. DC cannot pass through CE, it will only pass through RE. But for AC, C is like short circuit. So instead of going through RE, all the AC source will go to CE, and it's nearly equals to 0. Its resistance is nearly equals to 0. So ideally, we'll get the amplification of infinity. So, but in reality, we won't get that, because there's a catch here. We know that at PN junction of this transistor, there's some resistance, right? So when we didn't have this C and it wasn't short circuited, the RE was so big than RE, this resistance RE here, that it won't be affected, and we wouldn't need to account this in our calculation. But now when we put a capacitor here, this will act as a legit source of resistance. So we'll have to account for it. So our formula will then be, instead of our formula VL by VV, instead of minus RC by capital RE, it will be minus RC by RE, because that's the resistance that AC signal will see in series with this capacitor CE, right? So RL by RC plus RL. So this is the amplification that we were hoping for, and this is, if you are in TU, then this is what we used in our practical as well. So this is due to this branch. But now let's move on to this branch, and let's calculate what is VV, because it's not equals to VS, right? So we assumed there's some voltage VV at this point. So now let's calculate what is the voltage at this point. So for that, if we look carefully at this branch, here's a voltage source. It's connected to the ground, and there's a resistance R, right? So at this point, this C1 is short circuited. At this point, we know VCC acts as a ground, and I showed you the region. So one point R2 is connected to the ground, and also this R1 is also connected to the ground. So if you look carefully, they are in parallel to each other. So let's forget about this RE for a moment, and let's forget that there's some resistance here, because if we consider RE, then we also have to consider beta plus 1 RE to be base resistance, right? So, or let's just yeah, so let's forget about this for a moment. I will explain it later. So here here was our VV. So how to calculate VV? This the equivalent resistance of this circuit is R2 parallel to R1. So now these two are in series, so the voltage division, so voltage across VV is simply given by VV equals to R2 parallel R1 divided by RS, right? So this is said to be RS plus R2 parallel to R1. This is our voltage division formula. So if you consider this to be Rin, it will be Rin by RS plus Rin. So this is what we get for VV. Now we'll account for this RE as well. So this is like there's another voltage, there's another resistance, and that's going to the ground through this point at the base of this transistor. So it's simply a beta plus 1 RE, and the voltage at base is not at this point but at this point. So, and here's a resistance here. So instead of doing this, we'll put another resistance here, which is in parallel to R2 and R1 itself. So so this Rin becomes Re, small re, and sorry, not small re, plus beta plus 1 Re, and this is R2 parallel to R1 parallel to beta plus 1 Re, and this is the formula that we get, the ultimate formula, and this is what's given in most of the books. So our ultimate amplification from Vs is VL by Vs is simply Rin by Rs plus Rin times our base formula minus Rc by Re times the amplification due to this branch RL by RC plus RL. So I hope you understood it, and I hope I'm able to explain it properly. And if you want more of these videos, please do subscribe to my channel and keep coming back. So for the next time, bye bye.